In the previous lesson, we talked about conditional statements. So today we're going to talk about definitions and biconditional statements and how those relate to those conditional statements. So a biconditional statement is a statement where both the conditional statement and the converse are true. So we're going to test these two particular statements, the conditional statement and the converse, and if they are both true, then that statement can be written as a biconditional statement. So when we're talking about biconditional statements, there is a new symbol. So you might see this double-sided arrow between them, which means that it can be written as the conditional statement, where it's P then Q, or as the converse, Q then P. So it can be used either way. We also use the words if and only if instead of if then when it can be biconditional, and that can be shortened to the abbreviation IFF. So something very, very important is that when we're talking about things in geometry, definitions are always biconditional. So a definition can be used in any form. So if you know that the definition of a right angle is that it measures 90 degrees, then you can, if you know that something's 90 degrees, you can say it's a right angle. If you know that something's a right angle, you can say that it's 90 degrees. Definitions are always biconditional. So an angle is a right angle if and only if it measures 90 degrees. So we're going to take a biconditional statement and we are going to rewrite it as a conditional statement and its converse. So the conditional statement is going to go in the same order as the biconditional statement. So here you can see that it's a biconditional statement because of if and only if there in the middle. And whatever comes before it, if we're using those logic symbols, the first part is going to be the P and the second part is going to be the Q. So here we have a biconditional statement separated by if and only if. So to write it as a conditional statement, that's going to be P, then Q. So for the conditional, we're going to say if two lines intersect, then their intersection is exactly 1 point. So we're just rewriting that as a conditional statement. And it goes in the same order as the biconditional. The converse of a conditional statement is when you flip the order. So Q, then P. So here I'm going to start with if, and then I sometimes have to change my wording a little bit to make it make sense. So if we said if their intersection is exactly 1 point, we don't really know what we're talking about. So if two lines meet at exactly 1 point, then they intersect. So sometimes we do have to change the language a little bit to make a statement make sense in plain English. So that's how we can use that biconditional statement. So the original statement was biconditional, which means that it could use that new symbol with the double-sided arrow, and then we can break it down as a conditional statement and the converse. So next we're going to look at if we have a conditional statement, we want to figure out if it can be a biconditional statement. So here it says is the following biconditional statement true? It has the abbreviation IFF in the middle, which means it's a biconditional statement. And it says if the statement is false, provide a counterexample. So this says if x squared is less than 49, so x squared is less than 49 if and only if x is less than 7. So we have to look at both of our conditional statement and our converse of that statement. And if we can find a counterexample for either of those, then we can prove that this is false. So if we start with if x squared is less than 49, then x is less than 7. The other option is if, so that was the conditional statement. The converse would be if x is less than 7, then x squared is less than 49. So if we're dealing with x squared, we know that it can't go past 0. So if I think about all of those, and let's think about perfect squares just to make it easier on ourselves. So if x squared was 36, then x would be 6. That meets the conditions. If x is 16, x squared is 16, x is 4, that meets the conditions. If x is 4, x squared is 4, x would be 2. That one met the conditions. So I can't come up with a good counterexample here, and I know that x squared can't be negative. So if we're only talking about real numbers, we can't come up with a real number that won't make that one work. All right, so now let's look at if x is less than 7. So there aren't any bounds on x, whereas there were on x squared. So if x is 1, 1 squared is 1, that's still less than 49. But it didn't tell me anything about 0, 0 squared would be 0. It didn't tell me anything about the negative numbers. If I do -4, -4 times -4 is 16, so that one still works. But what about -7? So if x is -7, that's less than 7. But x squared, -7 squared, would equal 49, which isn't less than 49. So that one's kind of, a contradiction because it doesn't say less than or equal to, but we can go even further down and we can look at -8. So what if x was -8? So if x equals -8, -8 squared is 64. And 64 is not less than 49. So this would be my counterexample. And once I find one counterexample, that proves the whole thing false. So there were bounds on x squared, but there weren't any bounds on x, and I could just go anywhere less than 7. So I know that -8 is less than -7, or is less than 7. And whenever I square it, I get more than 49. So that's what breaks that biconditional statement. So we can't use that biconditional statement. All right, for example 3, we have a conditional statement. If x squared equals 4, then x equals 2 or -2. And we are going to write the converse, which this would be P, then Q. So for our converse, we're going to go Q, then P. All right, so if x equals 2 or -2, then x squared equals 4. Then we're going to look and see if this is true. And if it's true, we're going to rewrite it as a biconditional statement. If it's false, we're going to prove in a counterexample. So let's test both of these. So if x equals 2, then 2 squared equals 4. So that one works. If x equals -2, -2 squared also equals +4. Both of those work. So this is true. So since this is true, I'm going to rewrite it as a biconditional statement, which means that I'm going to use that if and only if. So whenever you do if and only if, you take out the if-then part. So we just start with the P. So that says x squared equals 4. And then for biconditional, we use that phrase. So if and only if. And then we put our conclusion. So x equals 2 or -2. So x squared is 4 if and only if x equals 2 or -2. The other abbreviation that you could use here is that you could say x squared equals 4 IFF, which means if and only if. And then you end it with that same conclusion. So both of these are ways that you can write a biconditional statement in words. In symbols, it is P *Q. All right, so this says write the converse of the angle addition postulate. The angle addition postulate we looked at in Unit 1, and it said if B is on segment AC, then AB plus BC equals AC. So that was where it said if you have a segment, you can add up two smaller parts to get to that whole segment. So when you find the sum of the two parts, it's going to give you the length of the whole line. So there is our angle addition postulate. We are going to write the converse. So if AB plus BC equals AC. We started with the conclusion, and then we're going to put that hypothesis in there. So then B is on segment AC. So I'm going to try to come up with a way that, see if I can come up with a counterexample. So if we had like two segments, like if they weren't all the same, I'm going to try to break it. So I'm going to try to come up with a conclusion. So if I try to make it like a triangle where B is not on AC, then I can tell that like this would like swing down and it wouldn't be the same. Those two together would be bigger if it was off of the line. So this makes sense. I can't think of any way that I would make this not work out. I can't think of any way I could put a point B not on that segment and it still add up. So that means that this is true. And so since it's true, we're going to rewrite it as a biconditional statement. So the biconditional statement is going to go with the original. So I'm going to go back up to this original angle addition postulate, and I'm going to rewrite it without the if-then and replace that with if and only if. So B is on segment AC if and only if AB plus BC equals AC. So we use that if and only if, or you could use that abbreviation here, IFF. All right, here's our last example. Write the converse of the statement. And the statement is if two angles are a linear pair. So that's my P. Here is my Q. So the converse is just going to flip the order of those. So when I write the converse, it's going to be if, and I'm going to start with the end part. So if two angles are supplementary. So I start with the end, and I do have to add in some words sometimes to make it make sense. So if two angles are supplementary, then they are a linear pair. And I end with what the other one started with. All right, so if two angles are supplementary, then they are a linear pair. So what I'm going to do is I'm going to see if I can figure out a way to make this false. So a linear pair are two angles that are adjacent and the non-shared ray forms a line. They're opposite rays. So I know that a linear pair looks like this. So they're adjacent, they share a ray, and then these two other rays form a line. And if I can think of two angles that would be supplementary but not be a linear pair, then I can prove this false. So what if I have those like same angle measures, but they don't touch? So notice that these two angles would be almost the same as the ones that I drew, but since I'm not using a protractor, I can't be sure. But since these are not adjacent, and let's make it stronger by throwing some numbers in there. So if this is 130 degrees and 50 degrees, that would add up to 180. So that's a linear pair that's supplementary. But this is a pair of supplementary angles. So they are supplementary, but they are not a linear pair. They do not have a shared ray. So these are not adjacent. So this would be my counter example, which is two angles that are supplementary but are not a linear pair. So that makes this false. So this one cannot be written as a biconditional statement. This right here, if two angles are a linear pair, then they are supplementary. This is called the linear pair postulate, and it is very important. So we will be using this a lot throughout the year. Get familiar with it, and since it's a postulate, It is not a definition. That means that it doesn't necessarily have to be biconditional, and here it is not.